Now, to our knowledge, all physical matter presents itself to us in one of three states. But you probably already knew that because water is a solid as ice, a liquid as drinking water, and a gas as vapor or steam. Now, there is a fourth and possibly fifth state of matter, and we will mention them in a moment. These states are often called phases of matter because a single substance, depending on temperature and pressure, can phase from a solid to a liquid and to a gas. As a rule, solids are more dense than liquids or gases with the same volume. And I realize that that last phrase made absolutely no sense, so let's talk briefly about those three items: density, mass, and volume. Yes, in acoustics, volume is the loudness of a sound. But in chemistry, volume is the amount of space something takes up. And if you want to measure the volume of something, scientists are fond of measuring it in cubic centimeters, which is exactly this big, a cube 1 centimeter on each side. You can see just how much volume a cubic centimeter takes up in comparison to, say, my hand. And just by looking, you can tell that this little block probably takes up about 2 cubic centimeters. And this one takes up, well, what would you say, about 4 or 5. They measure objects and say, this has a volume of 4 cubic centimeters. Or if the object is a weird shape and can't be measured easily, they'll drop it into a water glass with markings on it. They count the number of marks the water rises, and they know this object has a volume of 4 cubic centimeters. Our planet is practically covered with water, so water is a practical standard for volume and density. Water has a density of 1, so anything with a density less than 1 floats. Anything with a density greater than 1 sinks. This Diet Cola is less dense than regular cola because the regular cola has about 39 grams of sugar in it, and the Diet Cola has less than 1/4 gram of aspartame. Thus, one is more dense. It has more mass in the same space. Most solids are more dense than their liquid state. They shrink down and get heavier. In other words, the solid state will sink into the liquid state. The main exception to this rule is water itself. There are two theories as to what would happen if water acted like other substances. One says it would begin to freeze the top, become more dense, and sink down to the bottom. The top of the water would freeze again and sink to the bottom until every lake, river, and ocean in the world ultimately became a solid block of ice, and life on Earth would cease. The other theory says that the ice would form on the bottom of the lakes and rivers because the water would become more dense and sink as it cools. And again, all water would become a solid block of ice and life would stop. But neither of these scenarios happen because water was designed differently. At exactly 39.2 degrees Fahrenheit, water stops contracting and begins to expand, becoming less dense than the liquid water. As a result, the ice floats to the top, insulating the water beneath. The water below never gets below 39 degrees, and when summer comes, the ice on top has a chance to melt back into a liquid, and life continues. So mass is the amount of stuff that you've got. Volume is the amount of space your stuff takes up. And density is how tightly packed your stuff is into a particular space or volume. So, take this sponge. It has a mass or a weight of about 2 ounces or 55 grams and has a volume of, this much. But if I continue to compress it, it still has the same weight, 55 grams, but now it takes up much less volume. It has become more dense. The mass or weight of a U.S. aircraft carrier is about 200 million pounds. But it doesn't sink because it takes up a gigantic volume of space. The deck alone is longer than 3 football fields. As a result, even though it weighs 200 million pounds, you know that the density of an aircraft carrier is still less than 1. In fact, you know this without even asking anyone, because you have seen them float. So, as a rule, solids have more density than liquids, and liquids are more dense than gases. In a solid, the atoms or molecules are locked in and tightly packed in a regular pattern. Solids have a fixed volume and hold their own shape. They don't compress easily. Molecules in liquids are close, but not as close as solids, and they move freely past each other, which is why they pour easily. Liquids have a fixed volume, and they assume the shape of their container, but they are still held pretty tightly together. This is why you can fill a glass of water past the top of the glass. The molecules cling tightly together, but only to a certain point. Other liquids, like lighter fluid, do not have the same amount of molecular tension in them. It takes a lot of pressure to compress a liquid and make it more dense, but it can be done. The water at the bottom of the ocean is more dense than the surface water because it is compressed by hundreds of tons of water above it. Gases are the odd ones to us. Even though we breathe gases continually, still we can't see them or readily put our hands on them. Gases do not have a fixed volume. If you let them out of their container, the molecules disperse and fly out into the atmosphere. They will assume the shape of their container, unlike solids which hold their own shape. The theory says that molecules of gases are well separated and vibrate and move freely about at high speeds. Gases compress easily. You can compress a whole closet full of air into one scuba tank. These ideas of matter are collectively called the kinetic molecular theory of matter. The kinetic molecular theory of matter is based on at least 3 assumptions. Number 1, gases are made of molecules that are far apart from each other. In other words, most of the volume is empty space. Assumption number 2, each molecule is in constant motion, and the motion is different for each state of matter. Assumption number 3, molecules have no force until they run into the container wall and exert a force on it. Here you can see molecules running into the walls, exerting force each time they slam into the wall. Normally, these molecules travel 2 trillion times faster than you are seeing them here. See, you probably thought that the inflated balloon was caused by gas molecules exerting a constant pressure from the inside of the balloon. Kinetic energy theory says no. It says that atoms are in constant motion, and as the flying gas molecules strike the outside of the container, the result is what we call pressure.
But there are so many of them, and it is happening so fast that it looks like there is a static pressure exerting on the balloon. This theory is also known as collision theory, for obvious reasons. The energy of molecules is also affected by temperature. So, the hotter they get, the faster they move. For example, a light stick is a form of chemical luminescence. Inside a chemical stick is a non-toxic chemical called siloom. Siloom is sealed in a small glass ampule, which is placed into a larger transparent plastic container and filled with regular hydrogen peroxide, then sealed. When the light stick is bent, the glass ampule breaks and the chemicals mix, creating chemical light with no heat, sparks, or flame. When placed in warm water, the chemical molecules speed up and the light shines brighter, but for a less amount of time. When they are placed in cold water or the freezer, the molecules slow down and the light gets dimmer, but shines for a longer time. Although light stick chemicals are non-toxic, they can cause irritation if exposed to the skin, and any contact should be washed with lots of water. We mentioned a fourth state of matter, and it is a little strange and difficult to grasp. The fourth state is plasma. Normally, gas molecules are electrically neutral, equal electrons to protons. But put enough heat in, like electricity, and the electrons fall off the atoms and become ionized. The argon gas inside this ball takes on an electrical charge, electric gas. Now it will respond to electricity and magnetism, so it moves and can be directed. Like gas, plasma has no definite shape and takes the form of the container it's inside of. This is not to be confused with the plasma fluid in biology, which carries red blood cells, although it was the scientist Irving Langmuir who saw that just as plasma fluid carried red blood cells, so this electrical gas carried free electrons. Because of this similarity, he named this gas plasma. Natural examples of electric gas plasma include lightning, the sun, and auroras. So are plasma TV screens, fluorescent lights, and neon signs. They are objects filled with gas and ionized, making plasma, the electrified gas. And then there is that fifth state of matter called superliquids. If plasma is super hot particles, superliquids are super cold particles, so cold that the atoms almost stop any movement whatsoever. We will discuss the possible application of superliquids in the Future of Chemistry section. For thousands of years, people knew that vinegar, lemons, and other foods like that tasted sour. But it was only in the last few hundred years that we realized why they tasted sour. It's because these foods are acids. In fact, the word acid literally means sour. But what does it actually mean to be an acid? Throughout history, this lichen plant, called the orchella weed, has been used to dye fabrics a nice purple blue. Actually, it was called the poor person's purple because the deep, rich purples, called royal purple, were produced in small amounts from shellfish found only in the Mediterranean, and only the wealthy could afford it. Most sources tell us that it was none other than Sir Robert Boyle, the father of modern chemistry, who noticed that not only did this plant make a nice purple dye for cloth, But when the lichen powder was infused into paper, it turned colors when certain substances were applied. Specifically, when vinegar or lemon were applied, the paper would turn red, acid. And when, say, egg or seawater was applied, the paper would turn blue, alkali. The Scandinavians called this dye the staining lichen, or in their language, litmos, and Boyle's dyed paper became the litmus paper. For a definition, Boyle said that acids taste sour, are corrosive to metal, and turn litmus paper red. Alkalis feel slippery and turn litmus paper blue. As acid literally means sour, alkali is Arabic for the ashes, since burned plant ashes are naturally alkaline. Alkalis are often called base, though there are technically differences between the two. It was eventually discovered that acids increase the amount of hydrogen in the water, while alkalis decrease the amount of hydrogen, which helped explain why acids all have such similar properties. Around 1910, a scale was invented to measure for acidity. It is the pH scale and was invented by the Danish chemist Søren Sørensen, who is not to be confused with the Danish novelty inventor Søren Sørensen Adams, who was in fact the inventor of the hand buzzer, the squirting nickel, and the snake in the can. This was definitely a different Søren Sørensen. But the chemist Søren Sørensen is the man who invented the pH scale for testing for acids. The H definitely stands for hydrogen. But what does the P stand for? Incredibly, nobody is really sure what Sørensen had in mind, but most believe the P either means potential hydrogen or power of hydrogen, lowercase p, uppercase h. It is a scale from 0 to 14, measuring acidity, the amount of hydrogen ions. The closer to 0, the more positive hydrogen ions are produced, and the more acidic it is. The closer to 14, the more negative hydroxide ions are produced, and the more alkaline. And 7 is neutral. When an acid and a base combine, the single hydrogen atom and the hydroxide atom combine to form H2O, water, and thus are neutralized. By placing the litmus paper in the solution, it turns a color, and when compared to a chart, it tells you how acidic or alkaline the substance is. In addition to lichen plant, the juice from a simple red cabbage has historically been used as a fairly accurate pH indicator. Here's how they did it. Chop the cabbage. Boil it in water for about 10 minutes to release the dye in the cabbage. Then strain the liquid through a coffee filter, and you get a dye. And just like the lichen, red cabbage has a chemical that reacts with acids, making a fairly accurate indicator. Here we add it to a variety of house liquids: lemon juice, vinegar, baking soda, water, and bleach. Most solutions can be tested with this method. battery acids on the acid side, all the way to drain cleaner on the alkali side. Acids and bases are measured on the pH scale, developed by Soren Sorensen, the chemist. From time to time, you will hear about organic chemistry. Organic chemistry is the study of compounds that contain carbon, which means millions and millions of compounds. Carbon forms the basis of nearly all life processes. It was originally called organic chemistry because it encompassed only living organic organisms, but has since expanded to include other compounds like paints, plastics, petroleum products, many foods, drugs, and explosives. Organic chemistry is generally more dangerous than general chemistry because of the corrosive, toxic, and flammable nature of many organic compounds. Now that we have a better idea of how atomic theory works, I want to return briefly to the topic of radiation. The term radiation was coined by the Curies, and we used our fruitful analogy to show how pieces radiate off from themselves. But what is actually happening there? Well, we couldn't actually show that until we had a better understanding of the modern theory of atoms and the nucleus. There are actually two types of radiation: electromagnetic radiation and particle radiation. Electromagnetic radiation is pure energy with no weight, like sunlight and X-rays, like turning on the bedroom light. Electromagnetic radiation is really part of physics and doesn't directly concern us in Chemistry 101, though we discuss the X-ray work of Röntgen. Particle radiation are pieces of atoms flying off from the nucleus, like our fruitful analogy, decaying into simpler and simpler fruit, the radioactive decay chain. When they fly off, energized particles can knock electrons off of other atoms, including the atoms in your body, causing them to ionize. But the atoms and the molecules in your body aren't meant to lose electrons like that, and it can disrupt their ability to function properly or to function at all, and eventually they die. But why do atoms throw off pieces of themselves? The atom world is very stable as you look at the periodic table. Everyone happy and content, building bigger and bigger atoms by adding positively charged protons and neutral neutrons to the nucleus, all the way up to lead and bismuth. Then we hit element number 84, polonium, and the atomic world falls apart. Exactly why this is, nobody really knows in full. Every element has at least one natural or artificially made isotope in their family that is unstable and will undergo radioactive decay. Plus, nuclear physicists have made two synthetic elements having atomic numbers less than 83 to fill two gaps in the periodic table, number 43 technetium and number 61 promethium. Both of these are radioactive. But as soon as we get to element 84, these heavy nuclei can't seem to keep it together, and every last one of them from this point on are radioactive and start decaying, radiating particles and decaying down into the closest stable elements, lead and bismuth. An unstable nucleus continually vibrates and will eventually attempt to reach stability by one of three basic radiation methods: alpha, beta, and gamma, named for the first three letters of the Greek alphabet. To stabilize a heavy nucleus, like uranium, an atom will eject a set of two protons and neutrons. And as you can see, if a uranium atom with 92 protons loses two, it turns into a thorium atom, and continues to decay. Notice also that a set of 2 protons are exactly what make up a helium atom. And you will often hear chemists say that during radioactive decay, the nucleus loses a helium atom, and that's what they mean. These heavy alpha particles are easily stopped by clothes, paper, skin, or a couple of inches of air. But because they are very large and energetic, they can readily destroy delicate lung tissue if inhaled. Alpha radiation is encountered in radon gas, and most smoke detectors contain a small amount of the alpha emitter americium-241. Another way to restore balance to an unstable atom is to lose an electron if it has too many. But we are not talking about electrons that swarm around the atom. Remember, we are talking about the nucleus and nuclear decay. So, as strange as it sounds, modern physics theory tells us that a neutron inside the nucleus can actually transmute into a proton plus an electron. In fact, a proton can also change into a neutron and a particle called a positron. And when they transmute, the particles fly out of the nucleus and the atom changes into a different element. Now, if this sounds a little like the old alchemist days, you may not be far from the truth, because modern physics also tells us that a neutron is made of particles called quarks, and there are no electrons or protons hiding inside a neutron. Where the high-speed electron comes from is a bit of a mystery. Elements with an atomic number less than 83 usually will not undergo alpha decay, but they will undergo this kind of decay and throw off these high-energy electrons from the nucleus. This almost magical change in the nucleus and throwing off electrons is called beta decay, because beta particle was an old-fashioned name for an electron. If a proton transmutes into a neutron, you lose the one proton, and the atom changes into the element just before it. If a neutron transmutes into a proton, well, then you gain a positive proton, and the atom changes into the next element ahead of it on the periodic table. These high-energy electrons will penetrate skin, but are stopped by wood, plastic, walls, and thin metal. Even though they are not themselves radioactive, these particles act like small bullets and have enough energy to knock off the regular electrons in any molecule they come in contact with, including living tissue. X-rays and gamma rays are really the same thing, but are produced by different sources. Gamma rays are normally the byproduct from alpha and beta decay and are given off as an electromagnetic pulse. They have no effect on the mass or the charge of the nucleus, but they help stabilize the nucleus by releasing excess energy, very penetrating energy. Gamma radiation is the highest energy level of the three and is often called penetrating radiation. It is the radiation usually associated with fallout from a nuclear bomb. It takes a few feet of concrete or several inches of lead to stop gamma rays. The only difference between gamma rays and X-rays is how they are produced. Otherwise, they are identical. And they are found in the ionizing radiation part of the electromagnetic spectrum. In total, man-made sources of radiation account for only about 17% of background ionizing radiation, and this comes mostly from X-ray machines and nuclear medicines. About 83% comes from natural sources, including uranium, the soil, and the cosmos. This was the original International Radiation Symbol, invented at the University of Berkeley back in 1946 by a small group in the radiation department. Called a trefoil, it was supposed to represent rays radiating from a central atom, and it was originally a magenta symbol on a blue background. but it was changed 10 years later to black on yellow. Unfortunately, an international survey indicated that many children mistake this symbol for a propeller. So, the International Atomic Energy Agency announced a new symbol that would supplement the original sign. On a red background, it depicts the standard black trefoil radiating waves on a skull and crossbones, with a person running away from the scene, clearly indicating the message, danger, stay away, run away. But the trefoil is still the most widely used symbol of radiation danger. We will finish our discussion of radiation when we look at nuclear reactors, fission, and fusion in the Future of Chemistry section. That completes our overview of some of the basic concepts used every day by chemists all over the world. And while we have looked at all the major sections on the periodic table, each one of those amazing elements has its own unique story and fascinating facts about its design and placement in the periodic table. And those stories will be the theme of our next segments.